Today we're doing 4.9, point of inflection and concavity. Let's get started. It's stuck. There we go. Okay, so warm up. If I am given the function f of x, and I want to know where the relative max value is at, I would find the blank tangent lines. Okay, well, let's do that. Horizontal and vertical, right? I spelled that wrong. Vertical. Horizontal and vertical tangent lines. This is where the blank is equal to 0. The derivative of f is equal to 0. I think I said 0. I think I broke that down for you guys. Okay. To find whether it is a max value, I could plug some values from the blank and the blank into the blank. Okay, so to find out if it's a max value, I can plug in some values from the left and the right into the derivative. Yeah? If the value is blank, that means it's increasing. Okay, if the value is positive, the derivative is positive or greater than 0, another way that we've been saying it, that means it's increasing. If it's negative, or the derivative is less than 0, that means it's decreasing. Now, if my critical number is blank from the left and blank from the right, then I know it's a relative max. So if I have a max, that means it's going like this, right? Okay, so that would mean that it's positive from the left. So that means the first derivative is greater than 0 from the left, and negative on the right. That means it's going down. The derivative is less than 0 from the right. Then I know it's a relative max. Yeah. If it's opposite, then I know it's a relative min, right? Okay, let's learn some new stuff. Okay, first thing you need to learn is what is a point of inflection. Okay, in order to first know what a point of inflection is, you got to know what concavity is. Okay, so let me explain concavity real quick. Concavity, I have two ways of saying this. Concavity, concave up like a cup. Concave up means it looks like that. Okay, it means that it looks like that. Now you could just have one half of it or something, like that's concave up. And this is also concave up. Like it doesn't have to be the full cup figure. It just needs to show that it has that resemblance. Okay, concave down is like a frown, so you can imagine, hey, like that. Because you can turn that into a little dots. It's a frown. Okay, and it doesn't have to have the full frown. I mean, it could just be half of it, yeah? Or a portion of it. Okay, so basically a way of thinking about this side would be it's decreasing its slope's decreasing rate. Yeah, and you can define all of these in that sort of way. But a way I think of it is concave up like a cup, it looks like that. Concave down like a frown, it looks like that. Okay, so let's look at this graph here. Let's tell me where it's concave down. Okay, concave down, it looks like it's concave down this entire portion. Okay, all the way until right there, where it looks like it switches to being concave up for this entire portion. Okay, so concave up here, concave down here. Now a point of inflection is what we're going to be dealing with today. Point of inflection is where it changes concavity. It changed concavity right there. So that is a point of inflection. Okay, let's define that real quick. Point of inflection, so the x value, instead of saying where, let's say the x value concavity changes. Changes is the key word, okay? The concavity must change in order for it to be a point of inflection. And in order to look at this concavity, we need to look at the second derivative, okay? This concave down, if you look at the second derivative, which I showed you how to find the second derivative algebraically, it's easy. You just take the derivative twice. If your second derivative comes out to being negative, that means it's concave down. If your second derivative comes out to being positive, oops, I didn't put an equal sign there. Positive, that means it's concave up. Okay? If your second derivative, can't see that derivative sign. If your second derivative is equal to 0, that means it is not a point of inflection, but what we call a possible point of inflection. Because it doesn't mean that the concavity necessarily changes. Remember, concavity must change, but it means that it's a point where it could change. Kind of like a critical number. It doesn't mean that it's a max or a min, but it means it could be a max or a min. So we're going to be finding these points of inflection today. We're going to be doing algebraically. Okay, so let's try some of this out. Okay, so first let's just make sure you understand this whole concavity and point of inflection thing. So put a dot wherever you think it changes concavity. Okay, so I'll give you a second. Look at this graph over here. Tell me where you think it changes concavity. Okay, let's go over it. Right here, it looks like it's concave up because it's like a cup. And it looks like it changes somewhere around here. Yeah? It changed from being concave up to being concave down. Now, this is just kind of a guesstimation that I'm doing since I'm just looking at a graph. And we'll be doing it algebraically where we actually find the exact value where it changes. Okay, this part is concave down. Looks like it's concave down all the way until maybe around here is where it switches from being concave down to being concave up. So somewhere around 1. This one is somewhere around like -2.5. Okay, let's look at this one over here. So here, I'm gonna label them real quick in case you forgot what they were called. Points of inflection. Points of inflection. And that is where the second derivative does what? Equals 0. This is where the second derivative equals 0. Let's just remind ourselves, this portion right here is concave up, right? So if you were looking at the second derivative, that would mean that it is positive, right? This portion right here is concave down, so that means that the second derivative is negative. Okay, let's look at this. This is concave down, right? So that means that the second derivative is negative. And it looks like there's a point of inflection maybe somewhere around, like, I don't know, around -3. Looks like it switched from concave down to concave up. Okay, and then it's concave up this whole portion until, I don't know, maybe like around here, somewhere around 1. And then it's concave down the whole time, right? So these, again, are where the second derivative is equal to 0. These are the points of inflection. And these are where this is where the second derivative is positive and where the second derivative is negative. Okay, so if you can already take a guess at how we're going to be doing this, we're doing the exact same thing we were doing before with the number line, except instead of using the first derivative on this number line, we're going to be dealing with the second derivative. So here's your steps to finding a point of inflection, or just where something is concave up or down. Instead of setting the first derivative equal to 0, we're going to set the second derivative equal to 0. Okay, also don't forget about vertical tangent lines. Just like before, if it has a denominator, set it equal to 0. These are possible points of inflection. I call them PPOI, for possible point of inflection. Okay, set up your number line, label your PPOIs, just like we did with the critical numbers. Okay, so you're going to have your number line. You're going to get some possible point of inflections. Just like before we would label the critical numbers, we're going to be labeling possible points of inflection. Then you're going to be grabbing test points on the sides, okay? Test points. And you're going to be plugging those test points into the second derivative, yeah? And if your test point comes out to be positive, that means it's concave up right there, okay? Let's say you plug into the second derivative, your test point, and it's negative. Well, that means it's going to be concave down. And that would mean that this is a point of inflection because it switched concavity. This right here, let's say we plug into the last one. See, we plug the last one in here and we get a point of inflection that is negative again. That means that it would be concave down again, right? And that would mean that this is not a point of inflection because it did not switch concavity. It stayed as a negative concavity. So this would be your only point of inflection. Okay, write those steps down if you need them, and let's try out a problem. Okay, find the interval where the function is concave up and find any point of inflections, okay? So let's do this. And my justification, it says justify, my justification will be my work. Okay, that means I need to find the first derivative first. Okay, we bring down the 4. That would be 4 over 4, so it should be 1x cubed. Okay, go over here, multiply this. It's going to be 6 over 3, which is 2x squared, because we subtract 1 from the exponent, minus 2 comes down, 4x, because we subtract 1 off, plus the derivative of that is just 3, and the derivative of that is 0. Okay, now if I set this equal to 0, it would find critical numbers, and I'd be able to do the max and mins and the increasing and decreasing things with the number line. I don't want that. I want to deal with concavity and points of inflection. So I'm going to find the second derivative. So it's going to be 3x squared minus 4x minus 4. That's the second derivative. Okay, now I want to deal with concavity and points of inflection. So I'm going to do the number line with this derivative, the second derivative. So let's set up my number line. And let's find our possible points of inflection. So let's set this thing equal to 0. 3x squared minus 4x minus 4 equals 0. Okay, it looks like we're going to have to factor this. Looks like one of these will be 3x and the other one will be x. Okay, I mean, if you're me, I don't like doing these factors with the number in the front. So I use this cross method that I've shown you in the past. I'm going to write my factors of 4, so it can be 2 and 2, or it can be 4 and 1. Okay, I'm going to guess 2 and 2. Let's hope this works, so it makes it easy. 3 times 2 is 6x. X times that is 2x. Can I make the middle, which is negative 4x? Yeah, I can make this a negative and this a positive, right? I mean, this is negative and this is positive. Let's multiply these two numbers and make sure it equals this last number. Positive 2 times negative 2 is negative 4. There we go. There's my two factors, 3x plus 2 and x minus 2. Okay, so my possible points of inflection are going to be at 3x plus 2 equals 0 and x minus 2 equals 0, which is going to be at x equals negative 2 over 3 and at x equals 2. Let's put those down on my thing here, negative 2 over 3 and 2. And just like I told you to put critical numbers Cn under each one of these, I'm going to tell you the same thing here, possible point of inflection under these. And let's see if they are points of inflection, if they switch concavity or not. So we're going to need to grab some test points. Test point over here, negative 1 could be a test point. I mean, if you're not sure what value this is, just grab like negative 10 or something. Yeah, just make sure you're way over there. Point in the middle would be 0. Point to the right of this guy would be 3. Okay, we're going to plug these test points into the second derivative because we want to know what the concavity is at those points. So y double prime of negative 1, y double prime of 0, and y double prime of 3. Plugging all in our test points. Okay, now I could plug into this and figure out what it is, but there's an easier form of this to plug into. I did it over here. I factored it. So here, I'm going to write the factored form right under here so you guys can see this is what I'm going to plug into. Because this is going to be easier to plug these numbers into to figure out if it's positive or negative than this one. Okay, if I plug in negative 1, That's going to make this negative 3 plus 2. That's going to be negative times negative 1 minus 2 is negative. Okay, a negative times a negative is positive. So it looks like over here, this is concave up. Looks like this, concave up like a cup. Okay, now let's plug in 0. 0 would give us a positive right there, and it would give us a negative right there. And a positive times a negative is a negative. So it means that this is concave down. Concave down like a frown. So that means that this is a point of inflection. Get rid of that P at the beginning. This is a point of inflection. Let's find out if this one is. Plug in 3. That's going to give us a positive times a positive, which would give us a positive. That means it is concave up like a cup. That means that this is a point of inflection as well. So we have 2 points of inflection here. Point of inflection at x equals negative 2 over 3 and 2. Okay, now it also asks not only where there are points of inflection, but where is it concave up? Okay, let's tell it where it's concave up. Concave up. It's going to be intervals, okay? From negative infinity all the way to negative 2 over 3. So from negative infinity all the way to negative 2 over 3. Now here's something to remember. We've been using brackets on everything. With concavity, you use parentheses, okay? So it's from negative infinity to negative 2 over 3. And also from 2 all the way to infinity, right? Remember that 3, that's just a test point. We could have tested any point we want. Okay, so that's where it's concave up. That's where they have as points of inflection. If it would have asked where is it concave down, we would have said from parentheses negative 2 over 3 to parentheses 2. But it didn't ask about concave down. Okay, there's my answers. I hope you guys understood the lesson.